Here's something I want you to think about. You have been using electricity your entire life. Every morning you wake up, hit a switch, and light floods the room. You charge your phone, boil your kettle, run your laptop. Electricity is so ordinary, so woven into the background of everything you do, that you stopped asking questions about it a long time ago, maybe around age 10. And I think that is a shame, because hiding behind the most boring, everyday description of electricity, the one you learned in school, is one of the strangest and most beautiful ideas in all of physics. An idea so counterintuitive that when I tell you what it is, your first instinct will be to tell me I am wrong. So let me say it up front. The energy that runs your appliances does not travel through the copper wire connecting them to the power socket, not through the metal, not through the electrons. The energy travels through the empty space around the wire. That is not a metaphor. That is not a simplification. That is what the mathematics of physics has been telling us since 1884, confirmed over and over, and almost never mentioned in an introductory course. Let's start from the beginning. You learned something like this. A power source, say a battery, creates a voltage. That voltage is a kind of pressure. It shoves electrons through the wire the way a pump shoves water through a pipe. The electrons carry energy from the battery to whatever device is at the end of the circuit. The device uses that energy, and the electrons loop back to the battery, and the whole thing starts again. It's a tidy, sensible picture. Electrons in, energy delivered, electrons out. The wire is the pipe, the electrons are the fluid, the energy rides along inside the metal. And here is what I want to be clear about. This picture works. For calculating how big a fuse you need, for figuring out whether your circuit will overheat, for designing almost anything in a typical electronics lab, this model gives you the right answer every single time. The engineers who built the device you're watching this on right now used exactly this picture. Buildings are wired using exactly this picture. None of it is going away. But there's a crack in it, a specific, measurable, undeniable crack. And once you see the crack, you cannot look at a wire the same way again. When you flip a light switch, the lamp comes on immediately, not after a delay, instantly. So presumably, the electrons carrying the energy from the switch to the bulb must be moving extremely fast, near the speed of light perhaps. Let us find out. Take a typical household wire, say the kind inside the cord of your phone charger, about 2 millimeters across, carrying a modest current, maybe half an amp. Copper, like almost all wiring, contains roughly 8.5 times 10 to the 28th free electrons per cubic meter. That is not a typo. That is 85 followed by 26 zeros. In every cubic meter of copper, there are more free electrons than there are stars in 10,000 observable universes. Copper is absolutely stuffed with mobile charge carriers. Now, current is just charge flowing past a point per second. Half an amp means half a coulomb per second. Each electron carries about 1.6 times 10 to the minus 19 coulombs. So we can calculate how fast do those electrons need to drift to move that much charge per second through that wire. The answer is approximately 0.003 centimeters per second. Let me put that differently. About 0.03 of a millimeter per second. A garden snail moves roughly 300 times faster. If an electron started at your power socket and needed to reach the lamp on the other side of the room, 4 meters away, at this drift speed, it would take around 40 hours. By the time it got there, you would have gone to sleep, woken up, had breakfast, and gone to work. And yet, the light comes on the moment you hit the switch. How? The standard answer is clever and mostly correct. the wire is already full of electrons. When you push one in at one end, you don't wait for that specific electron to travel to the lamp. You just squeeze the whole crowd a little bit, and movement propagates almost instantly through the dense pack, like a shock wave moving through a queue of people standing shoulder to shoulder. One person leans, the next leans, the next leans, and 1,000 people down the line someone tips over before the first person has even moved noticeably. The electrical signal, the push, does travel at about 2/3 of the speed of light in a copper wire, fast enough that for any normal room, the whole thing appears instantaneous. But here is where the story starts to break down. The wire full of electrons explanation accounts for why the switch appears to work instantly. What it does not explain is how the energy gets from the battery to the lamp. In the marble in a tube analogy, when you push a marble in one end and one pops out the other, the energy travels through the column of marbles themselves. It hops from marble to marble, through the material. If energy travels through the electrons in the wire the same way, then it really is confined to the metal, to the copper. Energy in, electrons flow, energy delivered through the wire. But there is a troubling question this raises. A circuit is a loop. Electrons travel all the way around. At some points in the circuit, the electrons are receiving energy from the battery. At others, they are depositing energy at the lamp. But they are all connected, all being nudged by all the others. How does the energy know which direction to flow? How does it decide to go from battery to lamp and not the other way? The answer turns out to be the energy does not travel through the electrons at all. It never did. And to understand where it actually goes, we have to leave circuits behind for a moment and talk about fields. In the 1860s, a Scottish physicist named James Clerk Maxwell did something extraordinary. He took everything that was known about electricity and magnetism, scattered observations, partial rules, disconnected experiments, and unified them into 4 equations. Not 400, 4. And in the process, he noticed something nobody had asked for. His equations predicted the existence of waves, not vibrations in any physical medium, not sound, not ripples in water, something entirely new, oscillating electric and magnetic fields, each regenerating the other, rolling outward through absolute empty space at a fixed speed. He calculated that speed from known constants of electricity and magnetism and arrived at approximately 300 million meters per second. He knew that number. It was the already measured speed of light. Maxwell concluded that light is an electromagnetic wave, a shudder in the electric and magnetic field, propagating through the void, carrying energy across billions of kilometers of empty space with nothing to travel through except itself. That means electromagnetic fields carry energy, real energy, measurable, quantifiable energy flowing through space that contains no matter whatsoever. And once you know that, you have to go back and look at your simple wire carrying a simple current and ask a question you never thought to ask before. When current flows through a wire, there is an electric field along the wire, the field that drives the electrons forward. And there is a magnetic field circling around the outside of the wire, produced by the moving charges, exactly as André-Marie Ampère described. So around every current-carrying wire in the open space outside the copper, you have an electric field and a magnetic field coexisting. And Maxwell just told you that coexisting electric and magnetic fields carry energy. So is the space around the wire carrying energy? And if so, how much and in which direction? In 1884, a British physicist named John Henry Poynting worked this out precisely. He derived a formula, a way to take the electric field and the magnetic field at any point in space, combine them mathematically, and get a new quantity, a vector with a magnitude and a direction. The magnitude tells you how much energy per second is streaming through each square meter at that location. The direction tells you which way it is flowing. This is called the Poynting vector, and yes, it does point, literally. When Poynting applied his formula to a simple wire carrying current, what he found should stop you in your tracks. Near the surface of a wire, the electric field has two components. One runs along the wire, pushing electrons forward. The other points radially outward from the wire, created by tiny accumulations of charge on the wire's surface, charges that are almost never mentioned in introductory physics, but absolutely essential for making the circuit function. Meanwhile, the magnetic field wraps around the wire in circles, as André-Marie Ampère described. Cross those two fields together using Poynting's formula, and you get a vector that points radially inward, toward the wire, from the surrounding space. The energy is not flowing along the wire. The energy is flowing through the space around the wire, perpendicular to the wire, streaming inward toward the copper from every direction. At a light bulb, the Poynting vector converges from all sides into the filament. The energy arrives from the outside, not from one end, not through the metal, from the surrounding space, pouring in like water draining into a sink. The wire is not a pipe carrying energy. The wire is a drain. The energy lives in the space around it and flows in. Poynting was not alone in reaching this conclusion. Working at roughly the same time, Oliver Heaviside, a self-educated, famously difficult man who reformulated Maxwell's 20 equations into the 4 compact ones we use today, arrived at the same result independently and stated it even more bluntly. Energy moves through the field. The wire guides it. Heaviside had skin in the game. The great engineering problem of his era was the transatlantic telegraph cable. Thousands of kilometers of copper laid along the bottom of the Atlantic Ocean. Signals sent from Britain arrived in America smeared and distorted almost beyond recognition. The standard pipe model of electricity, championed by the eminent Lord Kelvin, could not fully explain why. Heaviside looked at the cable as a field problem, not a fluid problem. He recognized that the signal was propagating not through the copper, but through the insulating layer between the central wire and the ocean, through the electromagnetic field in that gap. The geometry of the gap, the properties of the insulation, the spacing, these determined everything about how the signal traveled. He developed the full mathematical theory of transmission lines, still used by every electrical engineer today. It is a theory about fields, not electrons. The Royal Society rejected his papers. He died in poverty. But every coaxial cable you have ever used, the one running to your television, the one on your internet router, works precisely because Heaviside was right. The energy in a coaxial cable travels in the space between the inner conductor and the outer shield, through the gap. The conductors are the walls of the canyon. The field is the river. Here is a thought experiment that makes the whole thing concrete. Imagine a very long circuit, a battery on one side, a lamp just 1 meter away from it, but instead of connecting them with a simple short wire, you connect them using wires that each stretch out 300,000 kilometers, roughly the distance to the moon, loop around, and come back. The lamp itself is still only 1 meter from the battery. The wires are just enormously long. Close the switch. How long before the lamp begins to glow?
If energy traveled through the copper, following the wire, it would have to traverse 600,000 kilometers at about 2/3 the speed of light. That is roughly 3 seconds. But the lamp is 1 meter away. The electromagnetic field begins reorganizing the moment the switch closes. In about 3/billionths of a second, the leading edge of that reorganization reaches the lamp. A tiny amount of energy begins flowing in, following the Poynting vector, arriving from the surrounding space, crossing the gap between battery and bulb directly. The lamp would glow dimly almost immediately, not at full brightness. That requires steady current all the way around the enormous loop, which does take seconds, but it is not dark for 3 seconds. The initial energy arrives through the field. The field cuts across the gap. It does not wait for the electrons to march around the long way. This is not a philosophical technicality. This is a quantitative, testable, measurable prediction that comes directly from treating energy as living in the electromagnetic field, not in the wire. If you still have a nagging sense that somehow the electrons must be responsible, consider alternating current. The electricity from your wall socket is not direct current. It does not push electrons steadily in one direction. It alternates, switching direction 60 times per second. The electrons in your wiring do not flow. They vibrate back and forth by less than 1/10 of a millimeter total, never actually going anywhere. Net displacement over time, 0. And yet, energy flows from the power station to your house continuously. Under the pipe and electrons model, this is incomprehensible. How do particles that go nowhere deliver energy from somewhere hundreds of kilometers away? Under the field model, it is straightforward. The oscillating current generates an electromagnetic field. That field carries the energy outward, guided by the wire, and deposits it at the load. The electrons shake, the field flows. The electrons do not need to travel anywhere because they are not the traveling part. This is not an edge case. This is how all power transmission works, and it connects directly to something even more striking: radio waves. In a transmitting antenna, the same oscillating electrons generate an electromagnetic field, and that field simply detaches from the wire and propagates outward on its own, carrying energy across empty space with no conductor to guide it at all. The mechanism is identical. The only difference is that in a circuit, the wire is there to constrain the field. In a radio transmission, the field is set free. Now, I want to be careful not to overcorrect here, because the overcorrection is its own kind of wrong. Some people hear this and conclude the wire is unimportant. Throw it away. The field is everything. That is not right either. No wire means no current. No current means no magnetic field around the wire. No magnetic field means the Poynting vector is 0. No energy flows. The wire is indispensable, not because it carries the energy, but because it sustains the pattern of fields that does the carrying. Think of it this way. A river flows through a canyon. The canyon walls do not carry the water. Nobody would claim that. The water flows in the open space between the walls, through the gap that the walls define. But take away the walls, and you do not have a faster river. You have a swamp. The water spreads uselessly across flat ground and goes nowhere. The wire is the canyon. The electromagnetic field is the river. The wire does not carry the energy, but it is absolutely necessary for the energy to go where you want it to go. This partnership shows up most clearly when you compare different types of conductors. A superconductor, a material with 0 electrical resistance, lets electrons flow without any losses, any friction, any energy absorbed by the material. The Poynting vector at the surface of a superconductor runs parallel to the surface. No energy enters the wire. All of it flows alongside it, in the field. Perfect guiding, nothing wasted. In a resistive wire, the Poynting vector tilts inward. Some of the field energy is absorbed into the metal, agitating the atomic lattice, generating heat. The more resistance, the more it tilts. The more energy is consumed. In a light bulb filament, high resistance by design, the Poynting vector points nearly straight in from all directions. Energy floods into the filament from the surrounding field, gets absorbed, and comes out as heat and light. The bulb glows not because electrons rush in carrying energy, but because the surrounding electromagnetic field pours its energy inward into the resistive filament from every side simultaneously. I can anticipate the objection. The simple model gives the right answers. Circuit boards still work. Fuses still blow at the right current. Why complicate things? Here is why. First, truth has its own value. If you want to understand nature, actually understand it, not just calculate with it, then the field picture is the true one, and the electron pipe picture is a convenient fiction. There is a difference between a map that helps you navigate a city and the city itself. Both are useful, but they are not the same thing, and pretending the map is the city will eventually lead you into a wall. Second, the field picture is the only one that works for the more advanced territory. Antennas, waveguides, signal integrity and high-speed electronics, electromagnetic compatibility, wireless transmission, all of these require you to think in fields from the ground up. Engineers who have been trained only in the pipe model hit a conceptual wall when they encounter these topics. Engineers who start with the field picture find that it all flows naturally from a single coherent framework. Third, and this is the one I find impossible not to mention, the field picture reveals that the seemingly empty space around a wire is not empty at all. It is full. It is active. Right now, wherever you are reading or watching this, every wire in your vicinity is surrounded by an electromagnetic field carrying energy through the space you're sitting in. You cannot see it, you cannot feel it, but it is every bit as real as the chair beneath you, and it is doing the actual work. The vacuum is not nothing. Maxwell showed us the field exists. Poynting showed us the energy flowing through it. Every experiment since has confirmed it. So here is the picture I want to leave with you. Next time you switch on a lamp, here is what actually happens. The switch closes. Almost instantly, a redistribution of charge occurs along the surface of the wire. Tiny accumulations of charge, constantly adjusting, which set up a structured electric field in the space outside the wire. That field, combined with the magnetic field from the current, creates a Poynting vector at every point in the surrounding space, pointing inward toward the wire. At the filament, where the resistance is high and the energy needs to go somewhere, that inward flow is greatest. Energy pours in from the field around the bulb, heats the tungsten, and light fills the room. The light is not powered by electrons shuffling in from the power station. It is powered by an electromagnetic field that exists in the air around the cable, carrying energy at nearly the speed of light from distant generators, converging on the filament from every direction at once. The wire did not deliver the energy. The wire made it possible for the field to deliver the energy. Those are not the same statement. And that distinction, small as it sounds, opens a window onto something remarkable. Energy does not require matter to move through. It rides in fields, in oscillations of the electric and magnetic field that propagate through space itself, needing nothing. The light from the sun that warms your face in the morning has been traveling through hard vacuum for 8 minutes before it reaches you, carrying every joule of that energy in pure field, in pure electromagnetism, in the very mechanism that also powers the lamp above your desk. It is the same physics. It was always the same physics.